In this example of using Lagrange's equation, I'm going to focus on 2 dimensions, and I will be using the polar coordinates this time. And to use the polar coordinates, I'm going to be using r and theta. Okay, r shows you the distance from the origin, and theta is the angle with respect to the positive x-axis. Now, for the kinetic energy, we know, of course, it's defined as it can be calculated in the classical physics approximation as 1/2 m the speed squared. Now, using polar coordinates, and what I recommend that you do in this case, if you need the speed in polar coordinates, in spherical coordinates, in cylindrical coordinates, simply look up a table in the book, either the front cover, the back cover, or somewhere else, and see what expression will give you the speed of a particle in the coordinates you need. In this case, I'm using the polar coordinates, and this is the speed is the square root of r dot squared plus r squared theta dot squared, and this is the square root, and because I have the speed squared, I have that, and of course the square root with the 2 goes away, so I have 1/2 the mass r dot squared plus r squared theta dot squared. Okay, that's my kinetic energy. For the potential energy, I will simply say that it depends on r and theta. I will not assign a specific function to that. I will just say it depends on r, theta. It does not depend on r dot and theta dot. Okay, the potential energy, there is a chance that this may depend on a velocity. I'm not saying that in this case. So moving on, the Lagrangian is defined as Ek minus Ep, and I'm copying and pasting what those are. Now here, minus Ep, that depends on r and theta. Now here, let's make it clear. L depends on r, theta, r dot, and theta dot. The 2 variables that describe the position of my system here are r and theta. Now that means I will have one Lagrange equation for theta, and one for r. Now, I'm gonna start to use this. I want to find the partial of L with respect to theta first. There is no theta dependence, there is no theta dependence, there is theta dependence over here, so this will be minus Ep minus the partial minus the partial of Ep with respect to theta. And I also need this term, the partial of L with respect to theta dot. Now, there is no theta dot dependence here, but there is theta dependence here, so this will be 1/2 m2 times theta dot, and this will cancel with that. Now, using all of these together will give me minus the partial of Ep with respect to theta is equal to d over dt m theta dot, and I just realized I forgot the r squared here, and that means I have an r squared here as well. And the only factor that depends here on time, well, I changed my mind. I'm not gonna do any work on this term with the derivative at this point. I'm gonna stop here. I will work on this when I'm done with the other equation as well. So for now, I'm gonna temporarily stop here, and to work with the equation, Lagrange equation on R, I need to find what this is. There is no R dependence here. There is R dependence here. So I have 1/2 m 2r theta dot squared, and there is some R dependence here as well. So this will be the partial of EP with respect to R. And similarly, I will do the partial of L with respect to R dot. And there is no R dot here, there is no R dot, the only thing is here. This will be 1/2 m 2r dot, so m r dot. Now I'm gonna take all of these together and I'm gonna combine them. The left side of Lagrange's equation is this. So copying and pasting. The 1/2 with the 2 will cancel out. So it will be m r theta dot squared minus the partial of EP with respect to R. And this is equal to d over dt of m r dot, and this will give me m r double dot. Now I'm gonna stop temporarily. I'm gonna stop here as well with this equation. If I give you an expression for the potential energy, you can find this partial derivative. You will get a result, and you will get a result here for this partial derivative, and plug them in and solve your differential equations for R and theta. That will give you the path, the trajectory that your system will follow. Now, instead of doing that though, I want to talk a little bit about what do these two equations represent, more conceptually rather than getting numbers down. Now, to do that, I will remind you of the following expression. In polar coordinates, the gradient, so this is the potential energy. The gradient of the potential energy in polar coordinates is the partial of EP with respect to R times R hat plus 1 over R, the partial of EP with respect to theta times theta hat. Now, I also want to remind you that the force and the gradient of the potential energy are related to each other. So the force is equal, in fact, to minus the gradient. So I'm going to include a minus sign here and here. So the force is given by this expression. And because this is what I have in front of R hat, this will be the R component of the force. And because this is what I have in front of theta hat, this will be the theta component of the force. What I'm going to get from here is the following. Fr equals minus the partial of EP with respect to R, and F theta is equal to minus 1 over r, the partial of EP with respect to theta. I'm going to use these two equations here to move on. I can see on the left side of this result, I have minus the partial of EP with respect to theta. And minus the partial of EP with respect to theta is simply r times the theta component of the force. D over dt, I'm not going to change that, mr squared theta dot. And let's see how that changes. So this becomes mr theta dot squared. Now I have minus the partial of EP with respect to r, and this is exactly equal to the r component of the force. And I will rearrange things here. So I will have Fr equals mr theta dot squared minus mr. No, that I made it. I have a typo. So this is the plus, and that means I have plus and minus here. All right, now we can start with this result, and I will simply go over this conceptually, okay? I'm not going to do any calculations. What I have on the left side, I see an r, I see a distance, if you want, and the force. This is what is related to the torque, okay? Remember, the torque is defined. Let me remind you. So the torque is defined as R cross F. Okay. Now, this only involves the component of the force and the distance from the origin. Of course, this includes the direction as well. But at the end of the day, you have a distance and you have a force, and this is related to a torque. Now, on the right side, I have a d over dt, so I have a time derivative. But mr squared is related to the moment of inertia. Moment of inertia, which we use the symbol I, and theta dot is really omega. And if you recall from introductory physics, the product of I times omega is related to the angular momentum, the spin angular momentum, but it is related to the angular momentum anyway. What the conceptual meaning of this is that this is what you would have gotten if you applied the angular momentum principle, T equals dl over dt, in this system. Okay, and we got this expression by not using any vectors and no cross products, no thinking about translational or spin angular momentum. We found this expression simply by doing partial derivatives of energies. Now here I have the force, the radial component of the force is equal to the mass r double dot minus r theta dot squared, and I want to point out what this is simply the radial component of the acceleration. So from here, essentially, qualitatively, conceptually, we have an application of Newton's second law with the force on the left, one component of the force on the left side and the acceleration on the right side. So it is interesting to see, though, that using polar coordinates in 2 dimensions and applying this theory of mechanics, you get results that you would need to use both Newton's second law and angular momentum to obtain from introductory physics.